Students.
Recording in progress.
Hi students. In this lecture, we are going to learn work energy power. First, let us see the list of concepts in this chapter. So first we discuss a definition of work done. After that, work energy theorem, conservative force, potential energy, law of conservation of mechanical energy, relation between conservative force and potential energy, types of equilibrium, vertical circular motion, and finally power. Okay, so these are the concepts we are going to learn in this chapter. So now let us see first of all what is definition of work done, right? Okay, let us consider a block of mass m placed on a smooth surface which is horizontal. Consider a block of mass m placed on a smooth surface which is horizontal. Suppose we are applying a force F horizontally on the block. We are applying a force F on the block horizontally. So initially block was at rest, means before applying force. When we apply force, now block moves. That means now block is having speed. That means we can say now block has gained kinetic energy. So we are knowing that when a body is in translatory motion, its a kinetic energy is given by half mv square, right? It is equal to half mv square. That is the kinetic energy of a body in translatory motion. That means because of applied force, body gain now kinetic energy, right? If we apply this force for more time, then it gains more kinetic energy. Or if we apply more force, then also that block gains more kinetic energy. That means work has done on the body. Work has done on the body because of which it gained kinetic energy, right? That means when we say work is done on a body, its energy changes. So here it is now kinetic energy of the body. So whenever we are saying work is done on a body, its energy changes. Now in this case, its kinetic energy has increased. That means work done by that force is positive. Or we can say work done by that force on the block is positive. Suppose I am taking like this. Assume that initially block was moving. Assume that initially block was moving and we apply force opposite to direction of motion. Suppose velocity is right side. Velocity right side, but we apply force left side. Okay. Now in this case, what happens is since net force is left side, acceleration is left side, but velocity is now right side. Acceleration and velocity, they are opposite. That means speed decreases. That means now here what happens is kinetic energy of the block decreases. So in this case, we say that work done by that force on the block is negative. In first case, because of the force, body gained kinetic energy. So work done by that force on the block is positive. But in this case, because of this force, its speed keep on decreasing. Means its kinetic energy is decreasing. Then we say that work done by that force on the block is negative. So whenever work is done on the block, its energy changes. If work done is a positive, its energy increases. If work done is negative, its energy decreases. So now we have to focus on how we are defining that work done. Because we are saying it is increasing, it is decreasing. But what is a way of calculating that? And that is given by work done by a force on a particle is given by F bar dot ds bar. See carefully. When a body is in translatory motion, for each and every point in that body, displacement is same, velocity is same, acceleration same. Means for each and every point, same displacement, same velocity, same acceleration. So we can replace the entire block with a single point, and that is what we call particle. So we are defining as work done by a force on a particle is defined as line integral. This is integration, but we are taking this over a path. I am repeating, we are taking integration along a line, means along which line that particle is moving. That's why this is called line integral, because integration can be taken over a surface. That is called surface integral. If it is taken over a volume, that is called volume integral. So now integration is taken along a line. That's why this is line integral. So line integral f bar dot ds bar, right? Now in this, suppose force is a constant. Then we can take f bar out of integration. It becomes now f bar dot integration of ds bar. Integration of ds bar. That means it is equal to f bar dot s bar. So this is if f bar is constant. Okay, right. See carefully how it is defined. Work done by a force on a particle is defined as line integral f bar dot ds bar. Okay, so in this ds bar corresponds to small displacement of the particle. It is small displacement, right? Okay, now coming to here, f bar dot s bar. From this, see what we can say. Since it is now dot product, work done is a scalar quantity. It is a scalar quantity. So this is equal to f into s into cos of the angle between them. Okay, right. Now this can be written as, either we can take it as f into s cos theta, or we can take it as f cos theta into s. See, as per mathematics, both are same. F into s cos theta, or it is f cos theta into s. But coming to in physics, the meanings of these two are not same. Even though values are same. See the meaning of this one. So here we are multiplying force with component of displacement. So s cos theta, this is component of displacement along force. But coming to here, this is a component of force along displacement, right? Let us now focus this two by taking a problem to get more clarity. Suppose on a smooth surface, there is a block of mass M, apply force F, that makes an angle theta with a horizontal. It makes angle theta with a horizontal. Suppose now displacement is S. So this block has displaced. Okay. Then what we are doing is here, we are taking F cos theta into S. Okay. So this is now what we are doing here. F cos theta into S. So we have taken component of force along displacement because the remaining component is F sin theta, which is balanced by, or you can say, along vertical there is no motion. So this F sin theta, EMG, and normal reaction upwards. So net value is 0. Okay, right. So coming to the second one, taking component of displacement along a force. For example, we can take a smooth inclined plane. Consider smooth inclined plane, which is a fixed. Release a block on the inclined plane. So here we are taking block inclined plane is a fixed. Okay, a block of mass m released from the top. Suppose a height equal to h. So here we want to calculate what is work done by gravity. That means a force is now gravitational force. Here gravitational force is now along vertical, right? But if you observe carefully, when block reaches ground, we want to calculate when block is reaching ground in this time gap, what is work done by gravity? So gravity is now constant force. So whenever force is a constant, we can take component of displacement along the force, right? Now see here what we can do. Suppose length of inclined plane is L, then displacement equal to L. Direction is, we can say this is A and this is B. Direction is from A to B, direction of displacement. So modulus value is Z, but force is now along vertical. So now here what we are doing is, we are taking now component of displacement along the force along vertical. Therefore, this is a theta. Now this angle is 90 minus theta, right? Component of this displacement along vertical, that is, let us call, let us take vertical down as y-axis. Then displacement component along y-axis, that is equal to L cos 90 minus theta. Okay, L cos 90 minus theta. Then by gravitational force, work done equal to. So since gravitational force is a constant, whenever force is a constant, we can take directly F bar dot S bar. Okay. Now we are writing F into S cos theta. We are taking component of displacement along force. So force is mg, that is downwards. And we have taken component of displacement, it is also downwards. It is now L cos 90 minus theta, which is equal to L sin theta. Right? That means this is example where we are taking component of displacement along a force. Right? And this is example for where we are taking force component along displacement. So like this, we can consider whenever force is a constant. Okay, right. And see here one more thing what we can say from definition part, F bar dot S bar. Coming to force, it is a frame independent. We have learned that force is a frame independent. Means in any frame, force will be same. But coming to displacement, it depends on the frame. Okay. That means work done depends on the frame. Work done is frame dependent. Let us understand this one by taking one example. Let us consider an elevator, or you can say lift, a lift which is moving up with acceleration U. Acceleration is upwards. Consider a block is attached to the ceiling of the lift. A block is attached to the ceiling of the lift, and mass is 7, right? Suppose we want to calculate tension in the string. We want to calculate tension in the string. Then see how much we get. If you want to calculate tension, suppose from ground frame. When we want to solve for tension from ground frame, see here I'm taking free ball diagram. So solving from ground frame, how many forces acting? How many forces are acting on the block? Tension upwards, right? EMG downwards. Acceleration is upwards, right? So acceleration upwards means net force is upwards. Then what we have to write? Net force, tension T minus mg. This is net force. Net force equal to mass into acceleration. Therefore, tension equal to m into g plus c. Okay. Now same thing. If you want to calculate, same thing. If you want to calculate from lift frame, from lift frame, from lift frame. See what we get. Lift frame means it becomes now non-inertial frame, right? So if you want to apply Newton's second law, we have to include pseudo force, right? So on the block, number of forces that are acting, tension upwards, mg downwards. Since acceleration is upwards, pseudo force will be downwards. So plus mu. And if you see from lift to frame, in lift to frame, block is at rest. Okay. That means net force equal to 0. Then we can write T equal to mg plus mu. T equal to mg plus mu. Right. That means we got same tension in ground frame and lift frame also. So here force is a frame independent, but displacement, it depends on the frame. Suppose if we see from ground frame, this lift is moving upwards, right? Lift moving upwards means block also moves upwards. That means block is having displacement with respect to ground frame. Therefore, by tension is upwards. Displacement also upwards. Therefore, by tension, work done on the block in ground frame is positive, right? But if you take lift frame, in lift frame, block is having no displacement, even though tension is same. That means S is 0. So in lift frame by tension, no work is done. I am repeating. In lift frame by tension, no work is done because With respect to lift, block is stationary. That's why work done is frame dependent. Okay. Next, we can take one small example like where between F bar and DS bar angle is always 90. So we have seen that if angle is acute, work done is positive, obtuse angle negative. If angle is a 90, then work done will be 0. Let us take one example for that. You can see in case of circular motion, circular motion, if you focus centripetal force is always towards center. Let us take it as F suffix C, centripetal force. And if you focus a small displacement, we are taking small displacement. Let us take it is now ds, small displacement. Small displacement means direction will be along the tangent, right? So if you take small displacements, it will be along a tangent between this displacement vector ds bar and this force vector means centripetal force angle is now 90. Okay. So if you take any small time interval or you can say any small displacement, it is always along a tangent direction of displacement and the centripetal force is always towards the center. That means work done by centripetal force is 0. Whether we consider one revolution or a half revolution or some part of the revolution, whichever part we consider in any time interval by centripetal force, no work is done because centripetal force is always normal to that displacement vector. See here why we are taking ds bar because the force is not a constant. So in this case, centripetal force direction keep on changing always towards center, right? Like this at this location. At this location, centripetal force like this towards center. At this location, towards center like this. So direction of centripetal force keep on changing. And angle between centripetal force and displacement is always 90. So whenever we are taking work done by centripetal force, it will be 0. Okay. Let us take now notes for this one. Right. So first one, definition, work done by a force on a particle. It is given as line integral f bar dot ds bar. ds bar is small displacement of point of application of force. If force constant, it becomes f bar dot s bar. It is scalar quantity. Next, it is a positive if angle is acute, negative if angle is obtuse, 0 if angle is 90. Next, and one more point here, area under force displacement graph with displacement axis gives work done by that force. So see this point once. See, we are knowing that integration gives area under the graph, right? See here definition part what we have given. Definition W equal to line integral f bar dot ds bar. So we are knowing that integration gives always area under the graph. For example, this is graph between force and displacement. Let us say graph is now like this, passing through origin. For example, this is corresponding to S equal to, let us say, 1 meter. And for this corresponding force is now take it as it is a 10 Newton. Okay. If they ask like initially force was 0, after having a displacement 1 meter, how much work is done? Then what we have to do here? So we are taking here integral F into ds into cos of the angle. Okay. Suppose in this between f bar ds bar angle is 0. Then this becomes now f into ds. So we are taking here one small displacement vector ds. Okay. This corresponding area is now. This is f into ds. Like this taking small displacement and we have to add all these areas. So this is what giving us work done. Okay. So area under force displacement graph with displacement axis gives work done by that force. So whenever I having like this integration, then we can focus. Integration gives area under the graph. It is now force displacement graph, right? That's why force displacement graph with displacement axis. That is giving us work done. Okay. Next. Next you can see units. It is just like force into displacement, right? So Newton meter, it is known as Joule, name of a scientist. So we have tried notation is capital J in SI system. Or if you take CGS, Dan centimeter or erg, and relation between 1 joule is equal to 10 power 7 erg. Okay. And coming to dimensional formula, ml square t power minus 2. See once carefully this, how we are taking this dimensional formula. So work done. It is if you take constant force F into S into cos of the angle. This is just a number. Focus F and S. When you take dimensional formula, coming to force, mass into acceleration, mass means capital. Acceleration is meter per second square. That means meter means L per second square t power minus 2. I am repeating. Force is mass into acceleration. Mass capital. Acceleration is meter per second square. For meter we are taking capital per second square. So t power minus 2 into s. S means again L. Okay. So this becomes now m L square t power minus 2. This is now dimension formula of work. Okay. Next. So next point it is work done by a force is a frame dependent because displacement depends on the frame. And last point, it is work done by centripetal force is 0 because force and displacements are always mutually perpendicular, right?